Okay, so what we have here is a spider mass ms hanging from a thread of spider silk. A fly of mass mf is hanging from another thread of silk below the stationary spider. The magnitudes of tension in each thread of silk T1, T2 respectively, as shown in the diagram. The the free body force diagram for the fly is also shown over here. So let's have a look here. Now, let me just rub this out. That is for later. So key idea is initially it's stationary. So that means that the net force on each spider and the fly is equal to zero. Forces are equal and opposite for each object. Now, we can concentrate on each insect and the forces on them separately. So the free body force diagram for the fly, you have the weight of the fly acting downwards, which is represented by the arrow here. The fly is represented as a dot, and then we have a opposing force, which is holding the fly up, which is this thread here, and that is T2, acting against the weight of the fly. So the weight of the fly, MFG, is equal to T2, and you can see that from the size of the arrows, they are exactly the same. Now, the free body force diagram for the spider, we have the thread that's above the spider is pulling the spider up and acting against the weight of the spider and the tension due to the pull of the weight of the fly. And they oppose the tension T1. And because they are stationary, I must draw these two arrows when they add them up inside. When you add them up in size, they must be the same length as T1. So as an expression for the second part of A, you can write down that T2 is equal to the weight of the fly when the object is stationary. And for the spider, T1 is equal to the sum of T2 and the weight of the spider, respectively, when the net force is equal to zero. The next part of this question is part B. Now, here you've got a spider producing more silk, and so that the length of the thread above the spider increases. So that length increases, and that will enable the spider to move downwards. So the spider and the fly both accelerate down towards the ground. So if the spider accelerates down towards the ground, I'm going to represent that with a double-headed arrow pointing downwards, as you often see in books. Assuming that the spider uh, mass of the spider, assuming that the mass of the silk is negligible, calculate the acceleration. So we're not associated any weight to the silk. So the only two weights that we're associating with are the weight of the spider and fly. So here we are going to begin with looking at the forces on the spider first and create a couple of expressions of the forces on the fly and the spider. Now, the net force is acting in the downwards direction because it's accelerating in the downwards direction. So that means that we look for the spider, we know that these are the forces acting on it. So when the spider is accelerating downwards, we know that the sum of these two forces must be bigger than the force acting against it. So in the expressions, we'll say that these two forces, the weight of the spider plus the tension T2, um, are greater, so minus T1 is the net force on the spider. Now the net force is therefore equal to mass times acceleration. So this is the mass of the spider times of acceleration. Why we said the mass of the spider is because we are concentrating on only the forces that are acting on the spider. So these are the only forces that are acting on the spider. So this is your expression for looking at the forces concentrating on spider. Next, the net force is equal to mass times acceleration. We're concentrating on the forces on the fly. Now, if the fly is accelerating downwards with the spider with the same acceleration, we know that the weight mf times g is greater than T2. So mfg minus T2 is the net force, overall force on the fly, and that equals the mass of the fly, because we are concentrating on the forces on the fly, times by the same acceleration. They both move in tandem with each other. Now, in this question, we have been given the mass of the spider, tension 1, the mass of the spider. So in this expression, T1 is T2 is unknown, and the acceleration is unknown. In this question, we do not know T2, and nor do we know the acceleration. So two things we don't know. So what we do is we rearrange this equation here. That's one way, to make T2 the subject, so that we can then substitute this expression into the first one, and that will get rid of the T2 and replace it with um, the weight of so mf times g plus mf times a. And that's what I've done here. So I just rub these two out. Okay. So in place of T2, I've put in this and substituted into 1, and we get this expression here. So now what we can see is every single variable, every single parameter within this expression I know, except acceleration. So mass of the spider, we know. Mass of the fly, we know. G is 9.81. T1 we know, and therefore we can rearrange for acceleration. So rearranging for acceleration, and then factorizing, what we see is that the acceleration is equal to the sum of the masses of each insect times by g. That would be the weight minus the tension T1, and divide by the sum of the masses of each insect. And putting all of that in, that gives us a value of 7.2 meters per second squared. Now, that seems like a reasonable answer. Why? Because if these insects were falling under free fall, they will be falling at 9.81 meters per second squared. We know that the thread is opposing the weight due to free fall, so there's some resistance there, and we're expecting the value to be slightly less than 9.81, and that is certainly less than 9.81, but nevertheless shows that the spider is accelerating downwards. Okay,